Hello and welcome. We have shown so far that the ferromagnetic Heisenberg model has a ground state model, has a ground state which is all spins up. If there is no magnetic field, of course, I could also choose all spins down. So, magnetic field actually chooses a direction, but nevertheless this is the ground state, this classical state, the intuitively correct state is the quantum mechanical ground state as well. And then I mentioned that AFM Heisenberg model is not so easy. The trouble comes trouble comes from the fact that the intuitive state, which is this is not even an eigenstate, and that is because if you operate by S plus on these spins, then it will not be 0. So, that means that that Hamiltonian that I wrote down operating on this will not return the same state even. So, this will become up, that means a different state. So, that is a big problem, and that problem is unsurmountable, almost insurmountable, and that is the reason we cannot solve Heisenberg model analytically except in one dimension where it was solved. That solution is of course a very famous solution, as I mentioned. Okay. So, there are numerical calculations people have done, and so those I will not get into. Okay. But those are only approximate in the sense that it is a finite site system where calculations have been done. So, as I said, the antiferromagnetic Heisenberg model is unsolvable. At least so far we have not been able to solve, no one has been able to solve in any dimension other than 1. The interesting thing about dimensionality, which I have been mentioned repeatedly, that dimensionality of the lattice where you are working in, the real space dimension where the spins are or the moments are sitting, is actually very important. And of course, the number of components of the spin that you are keeping, like in Heisenberg model you have x, y, z, all three components are kept, that is important. And so, the reason for that is that there are strong theorems, very important theorems, that tell us in which dimension with what kind of spin component, how many components of spin you can have a spontaneous magnetization or not. A famous theorem is that tells us all this is due to Marvin and Wagner, and this Marvin-Wagner theorem tells you that if you have your order parameter, which is say magnetization in this case, or staggered magnetization for antiferromagnets, in either case in dimensions 1 and 2 you cannot have ordered state, ordered state at for any order parameter which is continuous, in the sense that if you have more than one component of the order, like for example, if you have spins which have Sx, Sy both components, then you cannot have order in any dimension below 2. 6 Sy Sz if you have, then of course you do not have either. The only case, the case where you have order at 2 dimension. So, Ising model, for example, Sz has only Sz component, no other component exists. In that case, in 2D you can have spontaneous magnetization, spontaneous order. Okay. But not in 1D. In 1D we showed that at any finite temperature you do not have any spontaneous order. So this is basically the content of Marvin-Wagner theorem is a bit broader, but basically essentially for spin models that we are discussing, it tells us that for Heisenberg model and models where only x and y components are kept, you cannot have an ordered, spontaneously ordered state at any finite temperature for dimensions less or equal to 2. For Ising model, where only you have only one component, which is Sz, you can have order in 2 dimension, but not in 1 dimension, spontaneous order. So that is there are comments on this in many places. The book by Ashcroft and Marmin, the same Marmin, also makes a comment. You can go and look up. It is a very important theorem, and it is to be remembered when you do actual calculations, that this thing is this theorem tells us where to look for order and where not to. The reason for that, of course, is again fluctuations. Now, I will not get into the nature and details of fluctuations, but I will give one example where I will show how thermal fluctuation reduces the value of the total magnetization in a ferromagnet. For example, in this Heisenberg ferromagnet that we did, there are these fluctuations which can be actually calculated, and that fluctuation gives rise to a reduction in the total magnetic moment from its ground state value, which is a saturated magnetization, saturated value. From that you can, which is all spins up. So that is the saturated magnetic state, and which is the ground state for a Heisenberg ferromagnet. But once you are at any finite temperature, of course, this will start fluctuating, and the moment saturation value will not be the value of the total magnetic moment, and that is what I will just outline as to why this is important and how this is calculated. There are many ways to calculate this, very sophisticated methods exist. Here what I do is a method used, basically a classical method which works fairly well, but it gives the result which I want to show you. So, so spin excitations in the Heisenberg ferromagnet. Okay. So, what are the excited states? So, when the temperature is finite, of course, the ground state will have excursions into the spins will start fluctuating, and there will be excursions into the higher energy states, and that is what thermodynamics is all about. And so this description basically tells you how to calculate the energies of such states, what are these excitations, and so on. So in a ferromagnet, for example, a pictorial representation is like this, that the spins are starting to rotate. So if they were totally up, so spins were up originally, and now they start to rotate about it, and since they tilt and rotate, the magnitude starts decreasing from the saturation value, and so the net value will be, net magnetization will decrease from the saturation value. So this is these pictures actually show value from the way these fluctuations take place from the side view, and the spins from the top view you can see that the spins are rotating, and they are rotating with a particular wavelength lambda. So this wavelength can be very large, and the larger the wavelength, the lesser is the cost against such excitations. Every excitation costs energy. So it can be shown that as this wavelength becomes larger and larger, the angle between nearest neighbor spins is very small, then exceedingly small, and as the wavelength becomes very large, and therefore the even classically, if you think of the energy as S1 S2 cos theta between two spins, then if theta is exceedingly small, of course your energy goes as theta square, and you can expand cos theta and get a theta square term, and that is very very small if theta is small. So, these excitations, when they are quantized, are called Magnons. Now, a Magnon is basically a quantized spin wave. So, this kind of wavy structure of spin is called a spin wave, and this when you quantize are called Magnons. So, let us just try to calculate from this Heisenberg Hamiltonian. So, it is the classic the calculation goes classically. So, let us just go one more step. Okay. So, this again shows in a colored picture as to how these spins are rotating about their original around the magnetic field, for example, which is the original direction of the magnetization. And this is the wavelength, for example. Okay. Excuse me. So, let us just start calculating the ground state of a simple ferromagnet has all spins parallel, and then consider n such spins magnitude s on a line. So, let us do it for a one dimension, for example, on a line. So, and then you can rotate the put periodic boundary condition to make it into a ring, and the Hamiltonian here is only nearest neighbor. So, the Hamiltonian as we wrote down earlier for one dimension is minus j si plus 1, all higher neighbor interactions are 0. So, and then between I and I plus 1 the interaction is j. So, that is the simplest model, the nearest neighbor Heisenberg model in one dimension with ferromagnetism. That is what is being written down. So, these are vectors, and so that is the model we are going to study and try to find out its excitation spectrum. Okay. So, the classical derivation goes like this. Take for example, the ith spin. So, ith spin interacts with I minus 1 and I plus 1 on two sides. So, that means I can think of, like in mean field theory, I can think of the ith spin being acted on by a magnetic field that is coming from these two moments, these two spins, I plus 1 and I minus 1. So, that is the moment, that is the magnetic field that is written here, this H equal to I coming from I plus 1 and I minus 1 spins, and this is what we will use now, and we will just write the classical equation of motion, which is basically the force, angular momentum is changed due to the torque mu cross h, and that h is this. So, the ith moment has a torque on it due to the magnetic field coming from the two neighboring spins. Okay. So, that is equation is this, delta Si is. So, for example, for the ith spin it is I minus 1 and I plus 1 with Si crossed with Si. So, that is the classical equation of motion. In Cartesian, so divide it into Cartesian components. So, write the equation of motion for dsx Ix dt equal to some this is the result, right. It involves y and z components because it is a cross product. So, that is all you have. Okay. Similarly, you can write for sy and sz. Now, the assumption here is that these deviations from the z axis, the deviations, see in the ground state there was no x and y components, all z only. Once you start deviating, you generate x and y components. Now, if these deviations are exceedingly small, then the x and y components are very small. So, we will neglect all Sx square, Sy square, they are squares. Okay. So, that is what is the assumption here is. So, under that assumption, you can write down the equation of motion, which is these two will have see the Sx has y linear in y, and then the Sz is replaced by S, its fully saturated value, because the deviation from S is very small, as I said. So, at each site and each spin. So, this is replaced by S, and Sx and Sy are kept. But what is not kept is on the right hand side of Sz, the equation for Sz ds Iz dt, you had only x and y component, Sx and Sy components, right, and their products. So, the product is of order S square, Sx square or Sy square, or a combination of Sx and Sy, and it is actually a combination of Sx Sy, it is always like Sx Sy. So, these combinations are neglected, because both Sx and Sy are considered to be very small. So, their quadratic terms are neglected. So, that is why the right hand side here is 0. Okay. So, that is what is written here, Sx Sy product are set to 0, and Sz is taken to be S. Then of course, you can draw analogy with the phonon problem, for example, which is a very similar problem, where each site is coupled to the two nearest neighbors on its sides for vibrations. Remember your coupled oscillator. So, one oscillates, the other one comes closer, and so on and so forth. So, this is a very similar problem. There the coupling constant was k, potential was kx square. Here the interaction is j Si plus 1. So, that is the that's the difference, of course. These are two different problems. So, the analogy only is in this, the kind of equations you get, they are so Sx at ith site is coupled to its two nearest neighbors, Sy at ith site is also coupled to its nearest neighbors, and then of course, one can look for a travelling wave solution of this kind, and this solution is this and the other one, similarly for the other one. Now, put it back in. See, this is a general principle of translational invariance, because there is no site is unique in a Hamiltonian which is translationally symmetric, and that is being used here also. So, this once you deviate a spin, that deviation does not stay there, I mean that deviation moves, and that is these pictures actually tell you that the deviation is not localized, the deviation basically moves, and it the spin rotates. So, it goes through all the states. So, any deviation will pass through, the trough and the crest will pass through every spin. So, that is like a travelling wave, and that is because there is a translational symmetry. There is no spin which is a singled out, where you will only have the trough or the minimum. So, that is being used here, and that gives us this kind of equations, and it is a 2 by 2 matrix equation in terms of u and v, and you know how to solve such equations. All you have to do is to just diagonalize that matrix, that will give you the energy corresponding to these modes u and v. Okay. The modes that u and v combine to give you. So, there are this is the energy, and energy for the travelling wave, which is called the spin wave, and so this if you quantize will give you the Magnon. Okay. So, this is an energy which is very simple, h cross omega equal to twice J s into 1 minus cosine k a. So, k inverse of k is basically 2 pi by lambda, So it tells you what is the wavelength is. Smaller the k, the larger the wavelength, and so that means the less is the cost of the excitation, and this indeed is the case. You can expand the cos k for k much less than 1, k a much less than 1, you can expand, and 1 minus cos k is then half k a square, and this means that the energy is quadratic in k. This is different from phonons though. So, that is why I did not want to draw the analogy too far, because this is not really the same calculation that we are doing. In phonons this is linear in k. So here it is like a free particle, actually it is a k square spectrum, which is like a p square by twice m that we do. So 1 by twice m will be this 2 js half, so this js basically. So that is what it says, that in the same limit the frequency of a phonon is proportional to k, not k square. So this spectrum is therefore like this, okay, and a k square spectrum is generally termed as a free particle spectrum. Now once I have this spectrum, this energy, then I can calculate the in thermal equilibrium how many magnons are there at a particular temperature. So that is basically these magnons are bosons. If you quantize, you can see that they are bosons, and these the number is given by the Bose statistics, and the total number can therefore be calculated by the same principle that we used, the density of states of these phonons. See that these phonons have a k square spectrum. So they will also have a root over energy kind of a density of states, similar to what we got for free particle. So that is d omega here times this n omega, and here is the d omega being calculated. So then what you get is d omega is proportional to omega to the power half. Okay. So here of course what you have is you want to calculate this n of k, the total deviation from the number of so we were basically calculating the number of magnons. So that will basically tell you how much you have deviated from your saturation magnetization. So that number itself is the deviation from the saturation magnetization. So that is what one is trying to calculate, and so let us just see what you get. See, this is n k, sum over all k, and that is this, the integral becomes like this. You can convert it into a dimensionless integral, which is often done, and the integration can be taken from 0 to infinity, because the density of states vanishes, then the energies there are no phonons at infinite energy, no magnons at infinite energies, and so on and so forth. So all that is taken care of. You can take these limits from 0 to infinity. So then what you find is this kind of an integral, where this if you look at this last piece inside the integral, it's inside it's a dimensionless integration. Everything here is dimensionless. So this is just a number. All the temperature dependence is outside, and this is what you do in phonon in the device specific heat calculation as well. Then what you find is that there is a temperature dependence which is T to the power 3 by 2. This temperature dependence 3 by 2 was obtained first by Felix Bloch, the person in whose name Bloch theorem is, and he showed that there is a deviation from the saturation magnetization at finite temperature, and this number itself is the delta m, the change in m from the finite value, from the saturation value. and that number, if you calculate that integral, you can find this this numerical values are obtainable, and one finds kBT by Js to the power 3 by 2. So, this is the this is delta m by m. Okay. So, this is a dimensionless quantity on the left, should have a dimensionless quantity on the right, but the power of temperature is T to the power 3 by 2. So, this is called Bloch's T to the power 3 by 2 law, and it is confirmed experimentally. This is how the magnetization deviates at finite temperature in a ferromagnet, and this is obtained with neutron scattering. Okay. And this is this treatment you will find in Charles Kittell's book Solid State Physics, and in many other places, but there are, as I said, much more sophisticated techniques available, where you start by writing down the bosons, and then see the spin flip is like a boson. For example, take spin half, you are going from plus half to minus half or minus half to plus half, you are changing the spin by 1. So, this flip, if you can quantize the flip, you will see that it is a spin, it's a even spin object. So, that is it changes the spin by 1 basically, and that is even, and that will follow Bose statistics. The case for antiferromagnet is much more complicated. For AFM, first of all, we do not know the ground state except in one dimension, where it is not a state of that kind that I wrote up down up down up down, that is generally called a Néel state. Now, that is not even an eigenstate. So, let us forget about it, but the spin wave calculation is still done with respect to the classical ground state, which is the antiferromagnetic state, and one can calculate, then in that case one can calculate, and one finds that it is a more complicated calculation. The energy or the omega that we wrote here in this case will go as mod of k instead of k square. So, it is a steeper, so it is much more steep, it is like this, and that is E versus k for AFM, and that has profound consequences. And the only thing I would mention is that we are calculating fluctuations, but these are all thermal fluctuations. There are things called quantum fluctuations which are important, and for an antiferromagnet, for example, that already reduces the magnetization from its saturated value, and so those are beyond the purview of this course, but those who are interested can look up the literature and find out the case for antiferromagnet, which is a really interesting situation, and if you are really interested, you can look up. But as I said, that there is already in ferromagnet, there are these Magnons at finite temperature which will reduce the magnetization from its saturation value.